Hello, friends. How's it going? We've been crawling around a little while. We were thinking about trying to stand up and start walking. Maybe hit our heads a little bit here, and then we're just seeing birds around our eyes. Anyways, I know I'm kind of losing it here. It's tough for me to run through like four proofs back to back to back like this, but I'll give it a shot. Area of a triangle formula. Where does this freaking thing come from? Because it's pretty freaking close to the ones we just been looking at. Let's be honest here, okay? When you do problems out like this, you see the shape you want to get the area of here. Write the formula first, please, so that you don't think that the area of a triangle is simply base times height, because you got to cut that thing in half, okay? So b times h over 2, fine. This is the way your textbook does it, and this is the way I want you to think about it, I would say, too, because simply triangle's formula for its area is half. Okay, half. I put on the half thing here because a triangle is half of a parallelogram. What is the area formula for a parallelogram? Well, it's simply the product of its base times by its height, times by its altitude here, okay? So this is our formula, and just like the last videos, just like that. Just why you're here is because you want to hear the geometric justification for this. You want to hear the proof. Again, I'm not requiring people watch this year, but it might be kind of nice to see it and see how it all connects, okay? Check it out here. Again, I'm doing it, guys. I'm drawing some sort of generic triangle. So I'm looking for a scalene triangle where there's nothing particular significant about it. It probably just all cute, right? I probably don't want to do an obtuse one, but I could do an obtuse one if I wanted. But anyways, I'll do something that's scalene, right? Meaning no two of the sides are the same. Okay, let's do it like this. Sure, why the heck not? Well, it looks like it might be right over here. Let's maybe go, we'll do a cute. There we go. Okay, so that looks pretty scalene to me. Okay, there. Fits the definition of a triangle, right? We got three non-collinear points that are connected, coplanar points, three coplanar points that are non-collinear. We're connecting them through three line segments. Boom, we fit the definition of a triangle here. So how do we get to this thing here, okay? Because this is going to be our theorem, okay? So we need to prove it, okay? One thing to point out in this one here too, I always get confusion on this on problems, and you run into it here is, guys, it's not like a square. It's not like a rectangle where you can use side lengths, and just multiply them to each other to get the area here, okay? Because, I'll say it again, I said it in the parallelogram video. I think I also said in the rectangle video here, your h dimension is the height, okay, is the height. And the height isn't one of the lengths of the sides, unless it's a right triangle, okay, unless it's a right triangle, because one leg of a right triangle will also be that triangle's altitude, okay? Height represents the altitude to a particular base, okay? So if I'm going to call this my base, okay, base is just going to be a side, right? Just like the other formulas here, the lengths of one of the sides, I'm going to call this a base, okay? I'm going to call the base a base. Well, then what is the altitude? What's the height regarding that base, okay? If I had a B here, my altitude's going to be somewhere else. If I had a B here, the altitude would be like, that would be my altitude right here. But anyways, in altitude, we've known that definition for an altitude of a triangle longer than we have for an altitude of a quadrilateral or an altitude of a parallelogram. I just told you that an altitude of a parallelogram was like in the last video, right? Altitude of a parallelogram is the distance between opposite bases. Opposite bases, B, there we go. So H times B. So anyways, here, what the altitude of a triangle is the distance from an opposite vertex to a side, or the perpendicular segments, the length of the perpendicular segments from a vertex to the side opposite. And there it is here. I can only draw, it's not like the parallelogram, right? If I had a parallelogram like this, I get an altitude here, an altitude here, an altitude here, an altitude here, an altitude here. I get altitudes all over the place because we simply got to connect one of the parallel lines that contain a side to the other parallel line that contains its opposite side. That's it. So I can draw an infinitely many altitudes on a parallelogram. Here, I got one and only one, because an altitude of a triangle is the distance or the segment itself from the vertex of a triangle to its side perpendicular to its side opposite. Not to be confused with median, not to be confused with perpendicular bisector, although it's perpendicular. But anyways, not to be confused with angle bisector either. Okay, but this one isn't isosceles. There's nothing particular special about its altitude, except it gives us our h here. Okay, so the question is, how do I prove this? How do I prove this? Well, we've seen this. Hey, guys, we've seen this check this out. We've seen this b times h for parallelograms here, okay? So I'm going to write this before I even draw it, okay? Area of a parallelogram. I'm just going to use the formula equals b times by h. That's the formula here, okay? So given this diagram here, well, I'm going to say let that side be b, let this altitude equal h. Do you think I could change this diagram a bit to draw a parallelogram whose area is b times by h? Can I do that? Well, I can. Yes, I can, right? I can. It'd be easier if I had like construction tools. I can actually construct a parallelogram here. But no, you're gonna have to take my word for it. This is a parallelogram here. And I'm gonna be citing my reasons for that. First up, through a point outside of a line, right? We have a line here, line segment here. Through a point outside a line, there is exactly one parallel that I can draw in. Okay, that's how I would justify actually building a parallelogram right now. So I can draw a line parallel to, okay, let's say that looks about parallel to this line here. There, parallel there, parallel there. I can draw that in. Okay, that would be through a theorem. Actually, it's a theorem in chapter 2. Through a point outside of a line, there's exactly one parallel that I can draw through that point. That's parallel to that line. Okay, so I done that, but I also have from chapter 1, I have what? I have the ruler postulate, okay? I can take this length b, okay? And this length b, by the ruler postulate, it has a particular length that I can measure and assign a real number value to, okay? So this length b here has a real number value that goes with it. That means I could measure off a length of b, and I'm just gonna eyeball it here. What is that, 4, 5, 6? Okay, 1, 2, 3, 4, 5, 6. There we go. I can measure off 6 units up here, or whatever b is here. I can take that, measuring my geometry, an infinite ruler that I have, measure off a length of b, and replace this up here with a length of b up top here. Okay, you follow me? This is length of b right here, and then what can I do? I can finish my parallelogram, okay? Simply by drawing that in here. Wait, I did this wrong here. I was meant to go over 6 here. 1, 2, 3, 4, 5, 6, 7. I needed to go 7. I looked wrong. It was wrong. Okay, there we go. So that's length B. I duplicated length B. Now draw it down. Yeah, this looks much closer to parallelogram. Boom! Hooray! We have a parallelogram. How can I prove it's a parallelogram? Well, I have one pair of opposite sides where I measured out a length of B by the ruler postulate, so I know that B is congruent to this B, right? Any B is congruent to itself. So opposite sides are congruent, and they're also parallel to each other. I know because I drew the one and only parallel that would be through that point outside the line to this given line here. So I know by theorem that if I have one pair of opposite sides of a parallelogram where those opposite sides are both congruent and parallel, that my quadrilateral has to be a parallelogram. Hooray, it's a parallelogram here. Okay, and what do I know about this parallelogram? This particular parallelogram. Let's send the birds away for a second. I know that this particular parallelogram has the area of base, or B, right? Let the base of this be B, and let its altitude of that triangle be H. I know it has the area of B times by H. Okay, B times by H. Okay, check it out here. But I also know the area of this parallelogram. Okay, area of this parallelogram here is equal to, okay, let's let this be triangle number 1. Okay, triangle number 1. This one right here. Let that be triangle number 1 right here. And that's the one, right? Our goal of this is we're trying to prove the area of triangle 1 equals 1/2 base times by height, right? This is the triangle that we started with, where we have this altitude here of H, okay? Let's let that be triangle number 1. Let's let this other triangle, okay, up here be triangle 2, okay? So we're gonna get there through addition, right? Again, sort of skipping over stuff. This is just for you folks who want to get it proven so you know how everything connects, why this formula totally works. We can prove it to you right now. We got to use the area addition postulate, which I've skipped over in class entirely, but hey, I think it makes sense. Part plus part equals whole, okay? So we can do this. We can take, right, we can get this area of parallelogram 2 ways. One, I've already proven this theorem for you, that it's base times by this height, right? The same one as the altitude of this triangle. Hooray, we're gonna get to that a little bit later. But we also know that we have here area of triangle 2, okay, plus the area of triangle 1, which is the triangle we're trying to prove is equal to 1/2 base times height, okay? That is another way we can get the area of the parallelogram here, okay? Area as a product of base times by height, but area as a sum of the two congruent triangles. Because they are congruent. They are totally congruent. Yes, 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 they are. Why? Well, we know a few things. First of all, we know that this here is in both triangles. This side here, right here, is a diagonal of this parallelogram here. It's congruent to itself, okay, through reflexivity, okay? We also know that these two sides, we introduce parallel sides right here. We also know this diagonal is a transversal, okay, is a transversal here, running across this these two parallel sides, cutting two congruent. What kinds of angles are these? What are these called again here? Vocabulary check. What are these called here? Well, this is my transversal. They're not technically on opposite sides of the transversal. They look opposite. They're on alternate sides of the transversal. These are alternate interior angles. Alternate interior angles are congruent if they're if they're cut by parallel lines and transversal here. So lines are parallel, good. Transversal, good to go. Those are congruent here. So I know I have AS, but then I also have another S here. Okay, so it's not ASS. It's right here. It's what? It's S, okay? Because again, this is a parallelogram. Opposite sides of a parallelogram are congruent, but also we measured out B here, measured out B there. So here I have, okay, these two triangles, right? Triangle 1 is congruent to triangle 2 by SAS, by that reason right here, okay? By that reason right here. So what can we do? Well, I skipped over it because I'm not really doing the book right now, but hey, sometimes it's helpful to know where these formulas come from, get the mathematician's treatment to it. Because these are congruent, okay, there's the area congruence postulate, which I skipped over in section 9.1 because whatever, who cares? It's pretty logical here. If this triangle is the same exact thing as that triangle, they're just in different places, they're congruent to one another, then they have the same area. That's an assumption. And it's a pretty safe assumption. If you're the same freaking shape, you're going to bound the same area in the middle here, okay? So what do we know? We know that area of triangle 1 plus, by substitution here, by area of triangle 2, got to be the same as area of triangle 1 by the area congruence postulate here. That's another way we can get to the area of the parallelogram here. What's the area of the parallelogram here? Well, area of the parallelogram here is B times by H. Ooh, nice. What are we getting to here? Let's combine like terms. We have 2 times by the area of triangle 1 equals base times by height. Okay, what do we want to prove? We want to prove area of triangle 1 equals 1/2 base times height. What can I do to both sides? Well, I can divide both sides by 2 by the division property of equality, or what I can do, I'm going to do this. I'm going to multiply both sides by half because I like having that half. I like having that half in the formula, not the B times H over 2. I don't like that quite as much. Why? Because I want to be reminded, half of what? Half of the parallelogram that would get formed if you had a congruent triangle on the other side here, okay? So anyways, this is where it comes from. It comes from parallelograms. That's why I put that half in front. Half of the parallelogram. Half of a parallelogram that would have the same altitude and the same base, it's going to be half of the area. Therefore, the area of the triangle, triangle 1, or triangle 2 for that matter, is 1/2 base times by height, with this being B and that being H, the altitude, okay? That's my video. Thank you guys for watching here. Be careful about obtuse triangles here, because remember, obtuse triangles, the H is on the outside, because the H is the altitude, okay? Remember that. Altitude is the line that, the line segment that's perpendicular to the line containing the side opposite, okay? So this line containing the side opposite, we need to draw perpendicular to it. Oops, that's not perpendicular. We can go down here. So that's just one complication to using this formula. Is sometimes you get your H outside of the triangle. Thank you so much for watching. That's the 4th proof video. I'm going to make more of these proof videos. Why not? Let's see how it all connects together. Thank you for watching along with me. Birds spinning around your head too? No, hopefully not. I explained it so well, didn't I? Okay, thanks for watching. Email me if you have any questions. Bye.